Welcome back. Hopefully you had a good long weekend. Before we start any lecture, I had requests to postpone the exam by a week. And I want to make sure that I lay out the pros and cons and we make an informed decision. I am not opposed at all to changing it, but I want to make sure that nobody is disadvantaged, that nobody's upset, that you guys, ultimately, I want you to be happy. Let's see, Jenna and Claudia. So, the two options are stay with exam tomorrow and then group project day on February 18th, or group project day tomorrow and exam on February 18th. So, what would be good about postponing the exam for a week?
This week is
Claudia.
I'd be able to. Well, we'd be able to ask you a lot more questions because, like, even through like watching videos and things like that, sometimes it's just not enough. Because like I'll rewatch the videos and try to like go through the stuff, but I definitely think if we could do some of the worksheets together, because I'm like, I mean, it's just like doing it on my own. I'm very lost. So I think just like being able to ask more questions and it's like asking you and like being able to do it as a class is really valuable.
Okay. Other advantages. Isabel.
This week is kind of crazy. I have a lot of tests and other classes. So, and next week is kind of chill.
Sarah.
With Blank and lab last week, I think I showed a lot of us that we weren't prepared for the test.
Whoops, shouldn't have made that last mark. Well, I put mini and then part of it didn't show up. And so I tried to fix it and then the rest of it showed up. Up. Okay. What about things that would be better if we stuck with the schedule as it is now?
I was about to say we get it over with.
Get it over with?
There's only 2 days in the material.
Okay, erase that.
I mean, some people might, so.
That would bring their like other tests closer together, wouldn't it?
Yes. That's why I got out the schedule so I could look at it.
Yeah, when goes the next 2 weeks apart.
Yeah.
I'm so cool with that.
I mean, knowing it ahead of time kind of helps us.
Well, you've known for the last, 5 weeks?
No, I mean, if we change it and we
Oh.
know that the change is
Yeah.
happening this early, then it's not a problem.
Well, but you've known this exam was coming up for 5 weeks. So,
That's not the problem. The problem is that we're not getting material.
well, you have less time to adjust to that than you would have had for adjusting for this exam.
Would the scrapbook be moved with the test as well?
The scrapbook would be moved with the test, yeah.
Okay.
Because the point
So, no,
the point of the scrapbook is a fun thing to do as you review the ideas. Okay, so we've got things here on both sides of the ledger. I should have actually done a woo clap question. That way it'd be completely anonymous. But I didn't.
We can do
Think about
hands
it.
down. We don't.
Yeah, let's, why don't you just write on a piece of paper what you prefer, either test tomorrow or no test tomorrow. That way it's at least private, and then I'll tally it. I'm pretty certain I know how the vote's going to go, but I want to make sure that the students are making these decisions and not like, oh, he forced it on us. And of course, only one vote per person.
I mean, either way, it's gonna be rough. So, this is just a dose. But I definitely feel probably better.
I'll never know which one is yours.
I felt it.
I wrote two things.
You wrote two
I got confused.
contradictory things. Just cross out the one that keeps off. Okay.
That one's right. I don't know what those are.
Okay. So I will count here real quickly.
They're high in iron.
That's so cute.
Yeah, it's like cereal.
Yeah.
It's designed for babies, but because it's designed for babies, it has like all the
Okay. So we had 8 people. Oops, go back. 8 people here. 1 person here. 1 that said they don't care. And the 1 person who voted for having, or excuse me, I got those backwards. You're like, what? Sorry. And the 1 person who voted to have the test tomorrow said, but either way is okay. So with that, you have made the decision. Don't go blaming me or complaining to the academic dean. He postponed the test, and now we have 2 tests so close together, I have no way to prepare for it. Okay?
Thank you.
All right. So with that in mind, I'm still going to go through my little brief review. Tomorrow during lab time, I will be here to help you, as Claudia was saying, go over problems and that kind of thing. If you want to come and have more review.
And the group project is also.
Then the group project will also be postponed by a week. Yeah. Or excuse me. No.
This will be tomorrow.
Well, but the group project days are days we don't have lab. You don't have to work in the group project there. It's just a day we don't have lab so that you have time freed up. So you can schedule your time with your group whenever you like. Like some people are going to meet in the evenings, right?
Right.
But like,
So
But wasn't lab next week reserved for that group project?
right.
if we wanted to, can we do our group project that day too? So,
No, because we have to have the test.
Oh, no. We're talking tomorrow.
yeah,
She's referring to
because
tomorrow.
we're switching the tests. We're doing the tests not this week, but next week.
Right.
And so then if we're not doing a test in lab tomorrow,
Mhm.
can we also do our group project?
Right. If you don't want to work out, study whatever with me, yeah, sure.
Can we like schedule it where it's like half the time we study with you and then half the time we work on our group project?
You can schedule however you like. I'll be here.
So like it'll just be like open lab.
Yeah.
Okay. Sweet.
Okay, reviewing what will be on the exam now a week from tomorrow will be chapter 18, 19, 20, and 21. So chapter 18, that's where we learned about electric charge, the electric force, and electric fields. And so we start with the recognition that there is some strange force. And there's some strange force, then we introduce the idea of a charge associated with that force. Where are all my... Oh no, I took all my toys away for demonstration today. After I finish reviewing, I'm going to have to go grab my toys and bring them back in here. What was I thinking? Okay, so we learned about electric charge. There's two types of charge, so it's different from gravitational force. Because of the fundamental forces, the only fundamental force we had learned in all of first semester was gravitational force. And it had one kind of charge. What do we call that charge for gravitational force? No, the charge, not the force. It's something you know very, very well. Mass. Mass is the gravitational charge. It's the thing that the gravitational force depends on. And for electric force, we have the electric charge, which we usually just call charge. For magnetic force, the reason I realized I didn't have all my demos out here is because what we start with in my demos is demonstrating that there's a magnetic force and thus there must be a magnetic charge. And so the electric charge, we have two types because it was observed that you had some things would attract and other things would repel. Gravity only has one type that always attracts. And then we have the equation for the force, the electric force, that was identical to the equation for, identical in form to the equation for gravitational force. That is, the force electric is equal to K instead of G, Q1, Q2 instead of mass 1, mass 2, and then over the same R squared. Right, so it's a constant times charge 1 times charge 2 over separation squared in both cases. But you have the additional rule that opposites attract and likes repel, which we didn't have that rule for mass because it always attracted. And so what I just wrote is called Coulomb's law. And we have conservation of charge. Unlike mass, charge cannot be created or destroyed. And when you see that, you have to be careful. Electrons can be created or destroyed. Positrons can be created or destroyed. But if you create something with a negative charge, you have to also create something with a positive charge so the net charge remains unchanged. Whereas with mass, you can create mass. It's not conserved at all. So then we learned about electric fields. An electric field is completely analogous to gravitational field. First semester, I tried to mention gravitational field a few times, but we usually just said the acceleration of gravity. But that was the gravitational field. And so just like with gravitational field, the electric field was related to a force. The force electric is charge times the electric field. Just like force gravitational was charge times gravitational field. And notice I put M for the gravitational charge. So electric field, then we had some rules making it more complicated than gravitational field because gravitational field always points into the charge, into the mass. Electric field points into a negative charge and out of a positive charge. So different rule there on directions because we have two types of charge now. And then the force is, of course, in the direction of the electric field lines. Gauss's law, really, only one student's going to worry about Gauss's law. I'll talk to him tomorrow.
Yes.
Conductors and insulators. Make sure you know the difference between a conductor and an insulator. And so what's the difference? Conductors, the electrons are virtually free to move within the conductor. Insulator, electrons are in fixed positions. They can't leave their atom. Chapter 19, we had now electric potential and how it relates to the electric field. So electric potential, more commonly known as the voltage, is the electric potential energy per unit charge. So it's potential energy per charge, just like electric field was electric force per charge. It's a scalar, which is wonderful. Electric field is a vector. It gives you the direction of the electric force as well as the magnitude. By the way, do you remember with electric field lines, when electric field lines are closer together, what does that tell you about the electric field? Stronger. Farther away, it's weaker. Electric potential, we don't have field lines. We have instead equipotential lines or surfaces. Surfaces where the electric potential is constant, which means that there's no work done if you move along that surface. The fact that it's a scalar means instead of having to add electric fields as vectors, you can add electric potentials as scalars. Adding as vectors, break into components, add the like components together, then recombine using the Pythagorean theorem. Scalars just add the numbers. A lot simpler. And as once again, one student can tell you, once you know the formula for your electric potential, you can calculate the electric field anyway. So it's a lot more fun to work with electric potentials because it's going to take a lot less time in general to do the same problem. All charge naturally goes to lower potential energy, just like mass does, goes to lower potential energy. But for a negative charge, that means it's going to go toward higher voltage. Because negative charge having a negative value, a positive delta V times a negative value is a drop in potential energy. Remember that relationship, change in potential energy is equal to charge times change in electric potential. So electrons naturally go to higher potential and higher charge, more positive charge. Positive charges go to lower potential toward negative charge. Then we had capacitors. Really important that you remember, capacitors store energy, and then you can either describe it as in the form of a charge separation, as we have in the quiz, clicker things, WooClap, last class period, or in the form of an electric field. The capacitance is a physical measurement to tell us about the relationship between charge separation and voltage difference. And so it's based on the construction. So for parallel plate capacitors, which is the only type we talk about in this level of class, you have the capacitance is kappa, the dielectric constant. That tells you about how easily you can electrically polarize a material. Epsilon 0, the permittivity of free space. So kappa depends on the material. Epsilon 0 is a constant. Times the area of a plate on the parallel plate capacitor divided by the separation. Physical parameters. And then finally, the energy stored, just in case that U is confusing, potential energy is 1/2 capacitance times voltage squared. And then using this relationship that I circled, you can rewrite that in terms of like 1/2 Q squared over C as well. Moving on to chapter 20. We talked about circuits now. 20 and 21 are about circuits. Why? Well, electricity is important in lots of things, but electric circuitry is really important in a lot of things. And so we learned about current being the rate at which charge flows, and then Ohm's law, which doesn't apply to all materials, but it applies to a large amount of materials, that says that the energy that is required to make charge go through is proportional to the rate at which the charge is going through. In other words, the voltage drop is equal to some constant we call the resistance times the current going through. And of course, we did a lab where you tested to see if Ohm's law was correct. And the power dissipated, the amount of energy per second that is dissipated by a resistor, is current times voltage, or produced by power supply, current times voltage. What's the difference? Well, the direction. If the voltage is coming out of the positive side, it's producing power. If the current is coming out of the positive side, it's producing power. If the current is going into the positive side, it's absorbing power. Resistors always absorb power. Hence, for resistors, it always has to be like that. Power supplies should provide power. So a power supply should be like this. Remember, the long end is the positive, so I didn't write down positive. The current should be coming out of the positive on the power supply because it should be generating power. We learned about safety. it's an important thing to me to know about this safety, because if you're anything like me, now that you've taken general physics, you're going to feel a little more comfortable, like, oh yeah, we've got a plug that needs to be replaced. I can do that. But you need to be very aware of the safety issues. What should you do if you decide to change the plug? You should turn the power off. You should find the circuit breaker and turn it off. Some people, because it's often hard to figure out what's what, you can buy these little things that you can plug in that tells you if a plug is set right, and then you can press a button and it shorts it out. And when it shorts it out, what should happen? It should flip a circuit breaker. Circuit breakers, what we have right here. These things should, if you draw more than the applied current, it should flip the switch off, and then you have to reset it. And so by pressing that button, they know that they turned off the power to that one, and then they can work free of most concerns. There are always problems in wiring that can occur. I have had situations where I was working on a circuit where the power was turned off and got shocked because it was wired incorrectly. So it's still not safe. Be careful. And know these three levels. About 1 milliamp you can feel. About 10 milliamps will cause involuntary muscular contractions. And if you get 75 milliamps across the heart, it'll cause fibrillations. Why do we shock people if they're already having fibrillations? Yeah. The goal is to kill them.
You technically stop it, and so it can restart.
Yeah. You're trying to make the whole heart depolarize. And then hopefully it repolarizes, and they're getting hopefully a signal from the SA node. If not, remember the AV node should be giving you about 40 beats per minute. And even if the AV node is not giving its 40 beats per minute, the Purkinje fiber should still be firing off about 20 times a minute. And yeah. Oh, we had EKGs or ECGs. What's the difference in those two? I'm sure that will not turn up on a test question, but what's the difference in EKG and ECG? German versus English. Still electrocardiogram. What about EEG? Electroencephalogram. So that's when you got all the little wires burrowed into your little scalp so they can make contact and measure electrical signals in your brain. Okay, chapter 21. We had our circuits, our Kirchhoffs Laws. Kirchhoffs Laws, really simple. Kirchhoffs voltage law, the sum of the voltages going around a loop is zero. Basically, energy can't be created or destroyed. KCL, sum of the currents at a node is equal to zero. Charge can't be created or destroyed. We use those to solve complicated circuits. If it's a simple circuit, if it just has series and parallel, we can simplify resistors by adding them with the equivalent resistors. Now, you don't have to be able to derive. Remember, I derived for you how we get the equation for parallel resistors and for series resistors. But you should be able to calculate the equivalent resistor or equivalent resistance when you have like 5 resistors in some crazy series or some crazy arrangement. Keep in mind something like this. Whoops. Perfect. I wanted that one to go away. Something like this. No resistors are in series or parallel in that circuit. Because if they're in series, it has to be that any current that goes through one has no option but to go through the next one. There's nothing here where you have that requirement. Parallel, you have to have the tops connected together and the bottoms connected together. There are no 2 resistors here that have both the tops and the bottoms shared. So that has no series, no parallel. The only way we can solve that, based on what you know, is by using Kirchhoffs laws. You can't simplify that. As I was telling a student, well, you can use what we call a delta Y conversion to find equivalents for a delta, which is what we have there. But we did not learn that. More complication than we need. Make sure that you can describe how to use a voltmeter and an ammeter. Right? That you could have a question that asks you about how you're going to connect your voltmeter or ammeter. Voltmeter to measure voltage, ammeter to measure current. And then transient circuits, this will appear on exam 2. Because transient circuits, we have RC circuits, what we had right now that I talked about very briefly. You notice I didn't give you any homework to today, right? I didn't give you homework because we really didn't have any, I didn't demonstrate how to use the transient equation. I just showed you this is what it is and this is why. And so I really couldn't give you any homework on it. But transients will come again when we get to inductors. And so that's why it will be on the next test. We'll have both RC and RL transient circuits on the next test. Yes, ma'am.
So the independent linear equations have to equal every number of unknowns, right?
That's right.
It's like number of current that is unknown.
Yeah, the way we solved it, our currents were the unknowns.
And like the nodes is the number of nodes minus 1 to equal
The number of essential nodes minus 1. We usually just say nodes, like you said, but I'm the teacher. I have to be specific.
Okay. Thank you.
And the number of meshes is how many loops equations you can make. And you have to make sure loop equations cover the whole circuit. If you use the meshes, it will by default. You might have noticed one of your homework assignments had you do like the top loop and then the outer loop. But it still covered the whole circuit, so it was also a fair set. All right, to magnetism. I've got to get my demos back out here. I hope that they're still on the cards and I didn't put things away because I was all excited for the vacation cleaning up. Yeah, I they're on the card. All righty. How many people are familiar with a compass? Okay, a lot of people raise their hand. What does a compass do?
It has the little magnet inside that's attracted to the poles up here.
Okay, so here's the compass right here.
Maybe not a magnet. Is it?
No, it's a magnet.
Oh, it is.
That top thing is a magnet.
Okay.
And it's swinging around, it will slowly stop, and it orients itself pointing one direction. So we can use this for orientation. We can use this to figure out what direction something is, or what direction we're facing, etc. So that's my first, here's magnetism. Now, the story that I was taught when I was your age, which you know was a few months ago, was that a shepherd boy in Magnesia noticed that his metal-tipped staff would stick to some rocks. And so took out those rocks and playing around with them, and that was the discovery of magnetism. Magnetic rocks naturally occur. And so here I have just a regular bar magnet. Now I haven't done anything to check to make sure this bar magnet is what it says it is. But what I do know is it has two sides. And so I'm going to bring it over here to my compass, and I'm going to make the side that's marked S come here, and notice the blue side is pointing to it. Now I'm going to rotate this around so the side that's marked N is here. And now we see that it reoriented itself so the red side is pointing there. For those of you who are paying attention, what direction is north?
Apparently it's that way.
He says apparently it's that way. The people who are paying attention are pointing that way because it's that way. So this is not pointing the right direction when I don't have my magnet here. Is that what you're going to say?
Well, it mentioned, like, there was something in the textbook that, like, mentioned, it was something about, like, the needle not point, like, even though it's pointing north, it's actually, like, the southern pole will be actually thing.
Okay, that is also true. You can see that in the picture here.
Yeah.
The Earth, so in the early days, magnetism was one of the last things to be figured out by physicists before they thought they understood everything, which was 1900. Right before Einstein came out with his papers and they realized they didn't understand anything in that. So magnetism, they named one side of the magnet the north-seeking side, the side that pointed to the Earth's north pole. But then upon further examination, so now I'm going to make sure I have these things right. So I have up here, and we'll see some slides about this later, but these are what we would call soft magnetic materials. They're soft because I can make them change from one type of magnet to another type of magnet just by putting them in a strong magnetic field. And so that's what this is. This is a little device that will make a strong magnetic field. And I have written on here, because their words are a little confusing, put the south end of a magnet there or the north end here. So I want the north seeking side is the one we call north. So I'm going to put the north seeking side down there, and then I just have to make a loop between everything. Press my button a few times. And now I've made this into a correct compass. That's all it took. I say, now we test it. My dexterity with my right hand is less than with my left. My left disagrees. What? I'm a little confused because I should have put that in the right. I should have put that right, but it's still going the wrong direction. Try it again. Make sure I read this right. Yeah, no, I read it wrong. That's why I just put south and I put north in. Put south in there, try it again. So that's always embarrassing. So I'm going to do that a few times. I'm actually going to put, while I'm at it, put the south end of that one in there, the north end of that one in there, put this across the top, and do these as well. Make them. Okay, so now, I could just screw that up, right? Gotta have something in myself. So now it's pointing the other direction, right? Now, I oriented these in the same fashion, so now we can see what's attracted to what. So I'm going to first point the north side. I'll just bring it over here to the side and see which one comes to north. The south-seeking side came to north. What does that tell you? Opposites attract. So just like with electric charge, we have two types of charge here, a north and a south, and opposites attract. So let's take these two here, and let me give them to Jenna. So Jenna, just verify if you put north to south, do they attract? And then check what happens if you do north to north. Well, hold on.
Yeah.
So north to south attracts. What if north to north?
No.
No. Okay. Just wanted to make sure you have a student that you can trust, not a teacher who's into brainwashing you. No, we're not. No, we're not.
I wasn't even thinking it until I said it.
So we have two types of magnetic charge, north and south. So going to what Krista said, which you can see in this picture, they named the north side of a magnet because it was north seeking. It pointed toward the north pole of the earth. Sorry, Claudia.
No, it's fine.
Well, if I start calling you Ms. Nazario or Mrs. Few, because that's a lesson now, then we really have a problem.
You can just call me Bauermeister if you want.
Yeah, that's right. Bauermeister is what I was going to try to remember to say, because I won't mess that up. Until now that I've mentioned Krista's last names, her maiden name and married name. Okay, so because the north seeking seeks the south pole, that means that the Earth's north pole, and of course I changed my slide design, which means I have to change the colors I'm writing with. The Earth's north pole, so this is the north geographic pole, must be the south magnetic pole if the north seeking side of a magnet points to it. But I saw people put stuff away and I was out of time already.
Why did they do that?
They didn't know any better. Just like Ben Franklin arbitrarily chose for electrons to be negative. He didn't know any better. It's not until later on you find out, you're like, well, I guess we kind of have a confusing set of rules here, but hey, it's what we did.
So basically, it's because up is north. That's what they decided. So like they have the north and south,
Yeah.
opposite magnetic wise, And so because they're like, oh, I'm traveling up geographically, we're going to say that's north.
Well, north and south doesn't specifically mean up and down. In fact, you'll find people who get really bent because most maps show north is up and south is down. They say that's racist because it's, it's putting people who live in the northern hemisphere above people who live in the southern
Of
hemisphere.
course, you're going to have those movies.
It's silly because that's not the reason we do it. But there is also the fact that over 80% of all humans live in the northern hemisphere. But it still doesn't matter it's not meant to say what's on bottom is less than what's on top. It's just a cartographic standard. I've been watching Bonanza reruns, and in Bonanza they show Lake Tahoe, but they have north going like this. And I was like, that's not how Lake Tahoe's laid out until I realized the map is not following the standard.
So, do the people who want to equal the world, like with north pointing this way?
No. They of course make their maps with south on top. Because equality is never the goal. Supremacy is the goal, right? That's a little cynical.
I remember seeing that somewhere now.
Moving on.
Anyways.
Yeah. So, magnetism. What causes magnetism? There are two things that we think about, but they're all fundamentally, they're not all fundamentally the same. First, we have this thing we call spin in atoms. You guys have all taken general chemistry, right? You've learned about spin of atoms. What do you know about spin?
One is up, one is down.
Yeah.
Do you have spin up or spin down? What does that mean?
One is
If you spin opposite directions.
Does it have to do with molecular orbital theory? Because we're learning that again.
Well, what spin really does have to do with molecular orbital theory. So just a little brief history. When scientists were learning about the nature of atoms, they discovered that things like electrons behave differently, they have different energy levels if you put a magnetic field pointing one direction versus another direction. And so they said, aha, these electrons have a magnetic moment. That is, the electrons are behaving like little bar magnets. And they understood at this point that if you have charge going around a circle, it creates a magnet. We call them electromagnet. And so they said the electrons must be spinning around to create their magnetic moments. Upon further review, we now understand electrons don't spin. It's impossible for electrons to spin and create their magnetic moment as strong as it is. So spin is a misnomer. It's incorrect. Electrons do not spin. So we still say they have spin. We don't say they spin. And when we say they have spin, what that means is they have a magnetic moment. They're behaving like magnets. And the really weird thing, and this is a quantum mechanics thing, is that if you put an electron in a magnetic field, well, you saw here that north and south would be attracted to each other, right? If you do that with an electron, the electron has two options. It can be like this, or it could be like this. So you have spin up where it's mostly aligned, and spin down where it's mostly anti-aligned. But it will never be perfectly aligned, never perfectly anti-aligned. Those are the only two options, which is really weird. It's a quantum mechanics problem. And so spin up is when it's mostly aligned, and spin down is when it's mostly anti-aligned. And what they then do is they precess. They go around like this. The magnetic moments are going around the circle. And that's what leads us to nuclear magnetic resonance. Nuclear magnetic resonance is measuring that precession of the magnetic field. Okay, so that spin isn't exclusive to electrons. How many people knew that protons have a spin? Okay, a few. How many people knew that neutrons have a spin? They don't even have an electric charge, but they still have a spin. They still have an intrinsic magnetic moment. They behave like little bar magnets. And so the magnetism in things like iron, the magnetism that we see in iron we call ferromagnetism. Because ferro, what does that mean? Iron. Ferromagnetism is the magnetism like you see in iron. That's caused by the magnetic moments of the nuclei of the atoms. So by the spins of the nuclei of the atoms. Ferromagnetic, yes, it means iron-like magnetism, but we have other things that are ferromagnetic besides iron. Not all metals are magnetic, or not all metals are ferromagnetic. Nickel is ferromagnetic, cobalt is ferromagnetic, chromium dioxide. Chromium dioxide? Why does it have to be dioxide? It's more complicated. These are things that have strong magnetism. When I was a child, we would buy audio tapes so we could record songs off of the radio. I know this is very different from your world. And those tapes would say something like, Fe3 plus or CrO2. I was like, I don't know what that means. It means that's the kind of magnetic media they put in that tape. So there are other types of magnetism besides ferromagnetism. You also have paramagnetism. Para is a weak form of magnetism. And so things that are paramagnetic respond just like a normal magnetic material, but with a much weaker force, much weaker response. And then there's diamagnetism, which is really crazy. Now, I'm not going to do it because we only have 9 minutes left. But if you go to this video on YouTube, you can watch that little frog being levitated magnetically. They just put in a really strong magnetic field. Because just like you and me, what's the primary component of this frog's body? Water. And water is diamagnetic, which means it does the opposite thing. Instead of being attracted, it's repelled. And so you put that frog in a strong magnetic field, and it has a repulsive force that pushes it away from your magnet, and so you can make it levitate. And there are experiments indicated no damage at all to the frog, but it is kind of funny to watch it sitting there trying to move, and it can't because it's just in air and being levitated. So all materials have diamagnetic properties. The problem is diamagnetism is super, super weak. So paramagnetism will swamp out the diamagnetic effect. And of course, ferromagnetism will make it completely unobservable. Yes?
So they could levitate a human, theoretically?
Yeah.
Why haven't we?
I think they have. I think so. I'm not sure.
How is water diamagnetic?
It comes down to particle physics things that I've read up on it for class before, but I didn't this year, so I really can't answer. Now, when we talk about bar magnets, we don't think about those little magnetic moments. We think about instead magnetic domains. Claudia, Ms. Bauermeister had a question.
Thank you. This one high school teacher is probably a little bit. So it's ferromagnetism,
Strong.
paramagnetism, and diamagnetism.
Opposed.
How do you know something's diamagnetic?
Well, everything is diamagnetic, but you only observe it if it is not paramagnetic or ferromagnetic. Ferro is the strong one. Iron is strong. Okay, magnetic materials. What we do think about with magnetic materials is magnetic domains. So if I have something made out of ferromagnetic material, like this bar, it's made out of ferromagnetic material. Inside this bar, we have a bunch of little domains or regions where the magnetic moments of the nuclei are all aligned together. But you have these different domains, and on average, they're just randomly oriented. So on average, this is not magnetic. But if I put it in a magnetic field, it will cause these domains to change. Now, you'll notice that this here has these domains. This doesn't even have the same boundaries. So when it caused them to change, it also kind of gerrymandered, found new borders for the domains. But the domains, when you put in the magnetic field, they tend to align with the magnetic field. When it was like this, if you have a bunch of bar magnets that are randomly oriented, the net magnetism is 0. But when they're oriented together, it's not. So this would make something that's strongly magnetic. Now, some materials are hard magnetically. Some are soft. Soft means they won't maintain this alignment. they'll just re-randomize. So this here is intentionally something that's magnetically soft. If you put a magnetic field, it'll align and be a strong magnet. If you take it out, it'll just re-randomize and not be magnetic. These here are harder. They're still not magnetically hard, but they're harder, meaning if you make it magnetic, it'll stay magnetic at least for a while before it goes away. And things that are really magnetically hard, you make them a magnet and they should stay that way for a very long time. Right now I'm going to bring up how to store magnets, just in case you have magnets like this. I have some missing pieces. There's supposed to be a little piece of iron that goes in the top and bottom, keepers we call them. So that the magnetic fields, now we haven't talked about magnetic fields, but we have them in this opening picture. Magnetic field lines, if you notice, the bottom of the magnet was north, and the magnetic field lines are coming out of the north. So magnetic field lines come out of the north side of a magnet, and then they loop around, they go into the south side. And so the keepers should be put in here so I have the north connected, the north of one magnet connected to the south of the other. Because then the magnetic field lines go through that keeper. The keeper is made out of a soft magnetic material that will just orient itself with the external field, and it keeps the magnetic fields going in a circle. Now that's something different from electric fields. Electric fields, what was our rule for electric field lines? They go out of positive and into negative. For magnetic fields, in electric field lines, where do they start or end?
They start at the negative.
Okay, they can start at a charge, or they can end at a charge, and they can go to infinity. Magnetic field lines always form loops, always loops. They never have a starting or ending point. There's a reason for that. As far as we know, there is no such thing as a magnetic monopole. I said we have two charges. What did we call them for electric charge? Positive and negative. For magnets, we call them north and south. But unlike electric charge, you cannot find a north without a south. There's no such thing as a magnetic monopole, which would mean just the north. Now, something that you might say is, oh, come on, I'm no idiot. You have this bar magnet, cleverly labeled north and south. If I slice it in the middle, don't I have south on this half and north on this half? The answer is no. Every piece of this is one of those domains where it has both north and south, north on one side, south on the other. And you can cut it down as small as you want. You're always going to have north and south, which makes Gauss's law much simpler. Gauss's law for magnetism says the net flux is zero because the charge enclosed is always zero, which we will do. Okay. And everybody else is, why is he pointing to him? Because his life is harder than yours. This Curie temperature is something interesting. How do you make a permanent magnet? Now, I used this here, which just made a very strong magnetic field, to make semi-permanent magnets. But if you want it to be permanent, it needs to be magnetically hard. It needs to be something that is not going to be altered when you put it in a magnetic field. And the way to do that, first of all, you have to have the right material. But then if you want to make it magnetic, you can't put it in this because this wouldn't cause it to change its orientation. But if you heat it up to what we call the Curie temperature, named after, guess who? Yeah, I don't know if it's Pierre or Marie, but the Curie family. If you heat it up above that Curie temperature, even though it's still a solid, it's not liquid, it's not melted, magnetically it's free to rotate. So if you take a metal that's a hard magnetic material, hard meaning it is hard to change the orientation, you heat it up above the Curie temperature and you put an extramagnetic field, then it will align. And then you cool it down and it will stay that way for a very long time. Very long time, like thousands, hundreds of thousands, millions of years. And notice the temperature there. For iron, it's 770 degrees Celsius. I think melting temperature is around 1,000 Celsius, so it's a few hundred below. Question?
How do you get that hot?
A furnace. You There's lots of ways. If you use like a tungsten filament, tungsten has a very high melting temperature. And so you can make very hot ovens with a tungsten filament. Or, there's different fuels you can burn.
1500,
That's the melting temperature of tungsten or iron?
1538.
For iron. Okay. So that's about half iron's temperature then. Half iron's melting temperature. Okay. I am pretty much out of time, so I'm going to stop here, and we'll have more fun demonstrations in class on Wednesday.
And less fun activities.
Oh, that'll be fun.
No
So-
demonstrations.
Do remember